Okay, let's dive into this explainer and unpack this absolutely fascinating chapter. Together we're going to uncover how math is really just an epic search for hidden codes and patterns all around us. We're going to treat this whole chapter like a true detective story, where numbers and shapes are our ultimate clues. We've got a pretty clear map for today's investigation of the chapter. We'll start with the search for patterns, move right into fascinating number sequences, then visualize those numbers. After that, we'll uncover some surprising sequence relationships, explore the geometry of shapes, and finally, tie it all together with the grand mathematical connection. All right, part one, the search for patterns, finding the explanations. To kick things off, we really have to ask ourselves, what actually is mathematics? We're looking at a mystery so profound, it's propelled humanity to build bridges, cure diseases, and even send rockets to the moon and Mars. So if you thought this chapter was just going to be about rote memorization and endless calculations, do me a favor and just completely erase that idea from your mind right now. Seriously, that's just the paperwork. The crucial takeaway is captured perfectly right here. Mathematics is, in large part, the search for patterns and for the explanations as to why those patterns exist. You see, mathematicians are basically detectives. They're out there searching for hidden rhythms in nature, in the motion of the stars, and even in our genomes. It's this incredibly creative artistic endeavor just as much as it is a science. Which brings us to part two, fascinating number sequences, the basic clues. So, to crack this mathematical case, our very first set of clues comes from number theory. Now, this is the study of patterns in whole numbers, 0, 1, 2, 3, and so on. These number sequences are the absolute foundation of our detective work. And yeah, they might look simple at first glance, but trust me, they hide some truly incredible secrets. What's super interesting here is the sheer variety of patterns. You've got your standard suspects, right? Counting numbers, odd numbers, and even numbers. But as we dig deeper, we find triangular numbers, squares, cubes, and even the somewhat exotic Varahaneka numbers, where each number is built by adding the 2 right before it. Each sequence follows its own incredibly strict, distinct rule. Okay, moving on to part 3, visualizing the numbers, drawing the evidence. As any good detective knows, sometimes just staring at a list of numbers isn't going to cut it. You have to visually map out your evidence to truly understand it. Let's think about 2 specific sequences, square numbers and triangular numbers. When they're just written out as simple digits, 1, 4, 9 versus 1, 3, 6, they just seem like completely abstract symbols on a page. But this is where the chapter brilliantly illustrates why visualization changes literally everything. When we represent these numbers as dots, we see that numbers are actually geometric shapes. The sequence 1, 4, 9, 16 literally forms expanding squares, and 1, 3, 6, 10 visually stacks up to form perfect little triangles. So they aren't just names, they're physical descriptions of how quantities behave in space. And here is a totally shocking, delightful fact from the source material. The number 36 is incredibly special. It acts as a sort of mathematical shapeshifter. If you have 36 dots, you can arrange them perfectly into a sharp triangle, but you can also arrange those exact same 36 dots into a perfect 6 by 6 square. It plays entirely different roles depending entirely on the context. How cool is that? Let's jump to part 4, surprising sequence relationships. The interrogation. So what actually happens when we start mixing these basic clues together? Prepare to have your mind blown just a little bit. If we take our odd numbers and start adding them together sequentially, watch what happens. 1 is 1. 1 plus 3 is 4. 1 plus 3 plus 5 is 9. 1 plus 3 plus 5 plus 7 is 16. We are miraculously generating perfect square numbers every single time. It's not a coincidence. This pattern goes on forever. But why? Well, visualizing it provides the ultimate explanation. Imagine starting with 1 dot in a corner. To make the next square, you wrap 3 dots around it. To make the next square, you wrap 5 dots around that. Every new layer you add is simply the very next odd number. This beautifully explains exactly why adding consecutive odd numbers perfectly builds square numbers. And the interrogation of these sequences definitely doesn't stop there. What if we take basic counting numbers, add them up to a peak, and then add them back down? 1 plus 2 plus 1 equals 4. 1 plus 2 plus 3 plus 2 plus 1 equals 9. boom, we just uncovered yet another totally hidden path to square numbers. The connections are literally everywhere once you know how to look for them. This leads us right into part 5, the geometry of shapes, a wider conspiracy. Up to this point, we've been investigating one-dimensional and two-dimensional number sequences, but the rabbit hole goes much, much deeper into the physical world. We are now officially entering geometry. This is the branch of math that studies patterns in shapes across 1, 2, 3, or even more dimensions. And the exact same analytical logic we just used on number sequences applies here. We're simply replacing numeric digits with literal structures. Just like we had number sequences, mathematicians track sequences of changing shapes. Some of the most common ones investigated in this chapter include stacked triangles, complete graphs, the famous Koch snowflake, and regular polygons. By tracking these, mathematicians can actually watch how lines and angles mutate from one generation to the very next. It's fascinating to see how the chapter plays out these visual rules. Take the Koch snowflake, for instance. To get from one shape to the next, every straight line segment is repeatedly replaced by a tiny little speed bump. As this specific rule is applied over and over again, the shape grows infinitely more complex, with changes getting tinier and tinier. It's a strict, rigid pattern, creating absolutely incredible complexity. And finally, part 6, the grand mathematical connection. This brings us to our grand climax. This is where the world of physical shapes and the world of abstract numbers spectacularly collide. Let's think about the shape sequence of regular polygons. If we simply count the sides, the very first regular shape is a triangle. It has equal sides, equal corners, and it perfectly matches the counting number 3. The very next shape in this geometric evolution is a regular quadrilateral, which we commonly know as a square, and naturally that aligns perfectly with the number 4. That is followed by a pentagon with 5 sides, then a hexagon with 6, and so on. This proves a stunning reality. Shape sequences and fundamental counting sequences are bound together in an infinite, predictable pattern. The physical shapes we see and the abstract numbers we count with are really just two sides of the exact same coin. We've solved a lot of the mystery today, but the case is honestly never truly closed. Knowing that even the most basic counting numbers tell a vibrant visual story, what hidden geometrical codes might you be missing in your everyday life? Look at the buildings you pass, the tiles on your floor, or the petals on a flower. What other hidden patterns exist all around you, just waiting for you to be the detective and find their explanation? Keep your eyes open and keep searching.